evening. Welcome everyone to Ivy Tech. I've been here quite a few times, but some of you may be some first-time visitors, so welcome. This is one of our first-time visitors, right?
There's no way he's making it through this without talking. So go ahead and tell him right now.
That's okay.
My name's Jonathan Weinsaffel. I'm the chancellor here, and it's my honor to introduce Dr. Jon Schrage, who is our speaker tonight in the early college lecture series. Dr. Schrage has a PhD in atmospheric sciences from Purdue University. I do want to read through his bio because it's very impressive and it helps create the foundation, obviously, for his speech tonight. For most of the last 16 years, he has worked as a professor at Creighton University with joint appointments in the Department of Atmospheric Science, the Environmental Science Program, and the Energy Technology Program. There he taught a wide variety of courses in climate, meteorology, and renewable energy. He and his international team of collaborators have published numerous articles on the regional climate of Africa, including how climate processes affect the availability of water resources and the spread of various tropical diseases. For over 4 years, he was also the producer and host of Weather Break, a daily public affairs radio program about issues associated with weather, climate, and the environment. Jon now works for EVSC at Early College High School, which is housed right here at Ivy Tech, where he teaches a range of dual credit courses, including earth science, atmospheric science, and calculus. And as you can see by the title, Dr. Schrage is going to speak to us about climate change, what we know and how we know it. Frankly, I have found that this issue is one of the climate change, which is or represents an existential threat to the human race. That political and policy dynamics, which kind of govern its discussion, I find a little frustrating. and on the other hand, find very threatening to our way of life. And to not to be able to come to some type of consensus about the facts. Unless we can do that, we can never get to a discussion about how to deal with it, how to fix it, how to address it, how to cope with it, maybe. So I'm just excited to have Dr. Schrage here to make this presentation for your words of wisdom. Thank you. Thank you for joining us.
Jonathan. We have several of my students here who know that I have two things when I teach. I talk too much, I talk too loud, and I guess a third thing, I got too many slides. You will see all of those things tonight. The slides actually are just kind of distilled down from two courses that I used to teach when I was teaching at Creighton. A 100 level climate class and a 500 level climate class that we're just sort of distilling out right along this theme. Specifically, what do we know and how do we know it? Okay, because that's a legitimate question. I mean, you're going to go through life seeing all kinds of skepticism, but skepticism isn't an answer. I mean, you need to be able to somehow be able to sort out what is true and what to do about that information. So that's very much our theme here. I am not here to make you sad. We're not going to see pictures of drowning polar bears or starving babies or something like that. I'm not here to make you sad, but I'm also not here to make you feel good about it. To be honest, sad is a good reaction to climate change issues, okay? Well, basically what we're going to see is just a real quick why we need to care about climate change. And then I'm going to talk about 3 different kinds of lines of evidence that we have. We're going to talk about observations of the climate. We're going to talk about what the physics of climate tells us about what should be happening, and how we model or simulate future climates as well as the current climate. And then finally, we're going to talk about what isn't happening, what we can rule out, because you're going to hear all kinds of crazy ideas. Everybody's got a crazy uncle on Facebook, right? Everybody's got a crazy uncle on Facebook who has all kinds of crazy ideas. So I think what we should do is we should talk about why we care. Because plenty of people just plain don't. They say, how does this affect me? Why should I care? What matters? What will this have to do with any of us here? And I don't feel like I've given too much away yet to show you a graph like this that's showing different projections of future climate. Maybe we'll come back to this exact graph later in the talk. But different graphs of showing different predictions of future climate. And if you look at the y-axis on this graph, you can see that no matter what, we're expecting several degrees Celsius of warming over the remainder of the 21st century. Now, several degrees Celsius might not sound like all that much. I mean, plenty of places in the Midwest have these huge annual temperature cycles. You know, this happens to be Omaha in the background, just I had some kind of nice looking picture of Omaha. But, you know, the annual temperature difference between July and January is like 50 Celsius. Heck, for that matter, there's places on Earth that have daily temperature ranges between night and day of 30 degrees Celsius or more. As a consequence, it is not entirely crazy to ask, well, why do we care about these little temperature differences? What does 1.2 degrees Celsius of warming really mean? Or what does, oh, we're projecting 4 degrees Celsius by the end of the 21st century? It's not a crazy opinion to say, does that actually matter? Is that enough? Well, just to give a sense of how it doesn't take that big of a temperature change to make a big difference. If you wind the clock back merely 20,000 years to the peak of the last glacial maximum, global temperatures were only 5 to 8 degrees Celsius lower than they are now. In other words, the difference between northern Indiana is under an ice sheet 2 miles thick, and northern Indiana is one of the most fertile places to grow corn on the planet, is only 5 to 8 degrees Celsius. We have places on Earth that have already seen 5 degrees Celsius of warming since the Industrial Revolution. We'll see some examples of that in just a little bit. Okay? This is geologic scale change to be this much difference. Just to kind of make it more personal, back in 2003 I was living overseas. I was actually living in Cologne, which you see in the background right there. And in 2003 there was a heat wave. The summer of 2003 only averaged 3.5 degrees Celsius warmer than normal. Officially 70,000 people died of the heat wave in Europe that summer. Okay? This is excess morbidity, okay, right? These are people who didn't make it after a stroke kind of things, right? That makes a huge difference. That's only 3.5 degrees. Oh, it was miserable. I was living in this apartment with no air conditioning. I'm not happy about my living situation in the summer of 2003. Oh, but people say, surely this has happened before. It's all a cycle. Why, look how much we've warmed since the last ice age. Yeah, go ahead and talk to the megafauna you come across nowadays, how they feel. Oh no, they're all dead, right? It makes a big difference to them. Another point of view you often will hear, I just saw this on Sunday in Forbes or Business Insider or something like that. Well, maybe a warmer climate is better. Everybody loves a warm climate. No, warmer is not better. Warmer is not better. We and the animals and life around us are adapted for this place, for where we are right now, this moment. We are set up, not just adapted in like an evolutionary sense, but just in terms of the systems we've set up. Let me give you one example to dig a little deeper. Corn. We're in Indiana, we gotta talk about corn. That's where corn is grown right now. Right there. Okay, guess what? There is no reason whatsoever to think we're gonna keep growing corn in those places. Okay? Warming, just in general, might change that that's a great place for corn to grow, but more likely it's going to be things like extreme events. A single excessively hot day reduces yields. A insufficiently cold winter changes the makeup of the bacteria that lives in the soil, or the eggs that are larvae that overwintered. This may not be a place we can grow corn at the end of the 21st century. And you might think, oh, well, we'll just move it farther north. We'll just plant someplace else. Yeah, good luck with that. First off, raising corn takes a lot of infrastructure. There has to be places to store it. There has to be systems that can move it. There have to be people who know how to buy and sell it. But more importantly, there have got to be farmers. Farmers have huge institutional knowledge of how to plant corn, when to plant, what kinds of plant, what kind of herbicides. The people who live here don't have that. They have something else. Something else is already being done with that land, which may or may not be something we want to keep doing. The mere thought that, like, we'll adapt, don't get me wrong, we'll have to adapt to climate change. But the idea that somehow or other, we're just going to like, well, I guess you're going to learn how to plant corn, and the people in Indiana, I don't know, cotton or something, I don't know. It doesn't work that way, right? This just means suffering. And there are so many examples that, like, I could draw from the classes that I was teaching about climate to show examples, just to throw, okay, we already talked about heat waves. Heat waves are by far the biggest source of weather-related mortality in the United States. Okay? we don't want to have more extreme hot days in our climate system in the United States. The rates of photosynthesis in plants are controlled by temperature. The hotter it gets, the less photosynthesis that happens, the less the plants are producing food. And the parts we eat are generally the reproductive parts of the plants where those effects are amplified. So just a few degrees warming, if we didn't change what hybrids we raised and so on, would result in crop yields falling by 30 to 70%. We would have to adapt. But it would suck. Okay? It would be awful to have to figure out new things to grow and new things to eat and so on. Oh my gosh, what about security? We're first worlders. We'll probably find a way to spend money and fix our problems. The rest of the world? No way, they're gonna just get serious problems. It's called famine, it's called drought. We already have problems with migration, just over political problems, and the occasional famine, or the occasional drought, that leads to the occasional genocide, which we can just sort of mention glibly, like that's a little thing. But that's not a little thing at all, that's destabilization, that's wars we get drawn into, that's failed states we get drawn into. Yeah, we don't love that. I used to work on projects about diseases and global change. There's lots of diseases out there where both the pathogen, bacteria or amoeba or whatever, and the vector, the critter that spreads it, like mosquitoes or ticks, are related to the distribution of warming. Okay, it's usually pretty complicated how the two are related. But we used to work on the malaria project, but there were other people who did all these other diseases and so on. If the disease spreads to places where the health experts there don't know how to deal with it, that is a very serious problem. People die. Okay, people die from all these things. People die from bad drinking water. Drinking water is a hard thing to transport significant distance in the third world. We have big old aqueducts and things like that, and big old sewer separation projects that tear up the highway, tear up First Avenue for 6 months at a shot, but we have water on our tap. You know that's not the case for like half the people in the world, right? Okay? If they can't get water from the river, they don't have water. All right? This is a very big problem for lots of parts of the world. We can make it more close to home by talking about irrigation. Any place west about the Mississippi River could tell you about fights that already happen over water issues. Good luck getting that any better anytime soon. So these are all really horrible things before you even get to a drowning polar bear on an ice raft. I'm not going to go the whole direction of all the different ways ecosystems are getting messed up by all this. Yeah, don't worry about it. So let's talk about what we can actually know. Since we care, or should care, let's talk about what the evidence actually is. And the first kind of evidence I want to show you is observations, what we actually can measure and observe and so on. And there's, obviously whole courses about this kind of thing where we can talk about changes in precipitation or winds or storm tracks. But let's narrow it down to just temperature. Temperature is the one most directly related to the greenhouse gases that we relate, and it's also the thing that we just have best data about. It's relatively easy to get good observations of temperature. And since apparently we're hanging our hat on this idea that the planet is getting warmer, we better know where we get that information. And what I'm going to tell you is there's two main things that meteorologists use to get weather information about temperature. There's the so-called in situ observations. It's a Latin phrase that means like right here. And this is when we have instruments that are touching what they measure, thermometers. Okay? We're going to have weather stations. That's going to be in contrast, I'll show you a little bit, to the alternative, which is remote sensing, where the instrument isn't touching what it's measuring, like a satellite or something like that. Okay? But they have very different philosophical issues and so on. But we run networks of places we measure temperature. This happens to be part of the network that's run by the National Weather Service and the Federal Aviation Administration. We measure the temperature at weather stations a few thousand places in the United States, mostly regional airports. They're usually because they're co-located for things like flight operations. And so we gather weather observations. You might see one of these. Evansville's airport's got one. These are standard. They report every hour. And what I want to draw your attention to is there's a dude there. Okay? These things are professionally maintained. Somebody goes out and takes care of it and keeps it calibrated. There's a quality control procedure that quickly catches it if a windstorm knocked the thing over and it's laying in a puddle. Okay? These are high quality, calibrated, a couple times a month kind of observations. It's not just left someplace and just hope it's okay. So these are very high quality observations. And every hour, if not more often, it takes an observation and it radios into a system that quickly relays the observation all over the world. We deliberately archive these places everywhere before anybody's even seen it. Why? Well, nowadays we do it as part of climate change to make sure nobody's corrupting the data. There's no nonsense of anybody is somehow like, you know, those darn Chinese with their hoaxes. Or those darn liberal scientists who have, you know, what, no. Before anybody's touched the data, it's everywhere. It's in lots of different archives. So that very quickly we would know if anything's wrong, if anybody's tampering with the data. It's in lots of places stored separately. That's actually originally a Cold War thing. We wanted to share weather data. We have to actually under United Nations Treaty share weather data. We're very polite with our enemies in the Cold War. And this was how we relayed it. They didn't have to worry about there being like fake weather data being spread from one country to another. But we now use it for climate change. All these observations are quality maintained by the World Meteorological Organization, which is a part of the United Nations, and they are there to make sure that these are entirely consistent. All the observations are taken at the same time under very specific conditions with very specific data controls and so on going on, making sure that the data is high quality and homogeneous. We got the same kind of thing going on at sea too. We got meteorological buoys. There's a mess of them out there. We got merchant ships out there where a couple times a day, ships with appropriate training take weather observations. We get tons of those each day out from out at sea. We got lots of weather data. We also get weather data from satellites. That's that remote sensing strategy. You think about satellites, you think about satellite pictures and stuff like that. That's a big part of the story, but actually we can get all kinds of weather data from satellites too, like measuring temperature. In fact, temperature is one of the easiest things a satellite can measure. It measures radiation that the object is being given off. Here's a classic example, a map of sea surface temperature that satellites were measuring. Okay. This is actually extremely highly calibrated against the buoys that are the same location and so on. This is all very high quality data maintained ever since we've had meteorological weather satellites, since about the late 60s. We have fairly long archives of this kind of stuff. We have archives of surface weather observations in the United States going about to the 1850s. Other parts of the world back into about the 1700s. After that, we don't really have good ideas of thermometers, or we don't have good ideas of how their thermometer worked. And so we don't necessarily have good observations that much farther back. All right, so I don't think that's any shock to how we had to get those observations. The question is, what do we see from them? Well, I bet it's no shock. We see the planet's getting warmer. Here is a diagram that kind of shows over the last 100 years we've had this trend in surface temperatures averaged over the whole globe. Here's a similar diagram. I like this one better because it's got colors in it. When in doubt, always have colors on your slide. But we can see that, hey, wait, something weird was in the 40s, but whatever. If you think about the 40s, the last 100 years, something has clearly been wrong. That is not what the world should be doing. We're clearly in this giant global trend. The textbook that I got this particular diagram from says that this works out to about 1.3 degrees Celsius per century. That's a lot of warming. That is way into the range that we are in big trouble. Polar bears drowning. That's going to be a theme here. All right? And you don't have to go like to something really, exotic like averaging over the whole world. Here's Evansville. I made this last night. I just downloaded from a database Evansville's temperatures for the last 60 years or something like that, and had Google Charts make a best fit line on it, and that works out to almost 1.3 degrees Celsius per century. That's a lot of warming. I don't have to do any voodoo to this data. Okay, there's no fancy math here. It's the best fit line. Okay, holy smokes, that's a lot of warming. I just picked, Evansville because, here. It's very regional. Actually, if you look at a map globally of all the warming, you find out that some places are warming a lot more than others, especially the Arctic. In fact, some of these places over here have 0.5 degrees of warming, which sounds horrible until you realize the units are a degree Celsius per decade. That's 5 degrees Celsius in the last century, or 9 degrees Fahrenheit in the last century. No wonder they got the drowning polar bears. Yeah?
Wait, is the Antarctic the bottom? Or
The Antarctic is the bottom one, yeah. The situation in the Antarctic is more complicated than what's going on in other parts of the world. Notice that most of the warming is over land because God is punishing us. He's making it warm where we are. So what does the IPCC say about, I should tell you about the IPCC, the Intergovernmental Panel on Climate Change. These are the guys who got half the Nobel Prize a couple years ago. You might remember Al Gore got half the Nobel Prize and the other half went to this UN government organization. The IPCC was an organization set up specifically of a mix of scientists who were skeptical and who were believers, and said, we're locking you in a room for like 5 years, go through the data. And you know what happened? The people who were skeptical came around. Have you ever changed anyone's mind about anything? Good luck changing an academic's mind. If you've built your career writing papers about how climate change is wrong, bringing them around, that's a hell of a thing. Definitely worth a Nobel Prize. If you can get skeptics to come around and say, it is certain that global mean temperature is rising, that is crazy, okay? You got people who had made their career saying this wasn't right, coming around. They need a Nobel Prize. They need to be canonized saints. I don't know. They define virtually certain as meaning 99 to 100%, and this is actually more certain than that. They say that it is certain that the planet is warming, and it is very likely that the number of cold days and warm days are changing with fewer cold days and more warm days and so on. I'm going to just breeze through real quick here. I didn't want to spend much time on things like, obviously we know the oceans are getting warmer too. We know that glaciers are disappearing. It's actually quite horrible when you look at the graph of glacier length average over the whole world. It's terrible. It's not so great on this graph because you can't really see that axis very well, but we lose sea ice at a rate of 3% per decade. Not good. Ice sheets on land, like this happens to be Greenland's ice sheet over the last, well, this ended in 2010, this is monitored by a satellite that eventually deorbited and crashed. But anyway, you can see how that you can do that actually with stations at the end of the glaciers too. Hey, well, I'll answer your question at the end, okay? No, it is not great. But what I want you to take home from this, a philosopher of science would say what matters here is the consistency. It isn't like some things are saying yes and some things are saying no. Anything we look at says the planet is getting warmer, and by about the same amount. That is scary. Well, it's also kind of good. I mean, it tells us that we're on the right track about all this. It tells us with great confidence that the warming is real. Well, if observations are telling us the planet is getting warm, there should be some physics that tells us why it's getting warm. Now, anybody who's taken a physics class knows that there's a mess of these rules about radiation and heat moving through Wien's law and Stefan Boltzmann's law and stuff like that. And I decided to dwell on the delightfully named Beer's law, which sadly has nothing to do with beer, but has to do with I think he was a South German scientist named August Beer. Probably was Beer, not beer. But let's work with a clip art of beer. Beer's law is about how heat and radiation moves through material. And it is one of the fundamental tenets of modern science. It is how your dentist x-rays work. Nobody's crazy uncle says that the x-rays he got taken of his teeth are fake, or a Chinese hoax, or just liberal scientists who want to sell more fillings, right? Transfer of the x-ray radiation through your jaw is an accepted piece of science. We understand how it works. Your microwave oven works by Beer's law. I don't know what the heck they're cooking in here. It either looks delicious or horrible. But how your microwave works, how the radiation penetrates into the food and changes the temperature, that's Beer's law. Nobody thinks how your microwave works is a hoax. Okay? Check on your uncle if he thinks that it's have someone check on him if he thinks that that's a hoax, right? Your cell phone works. How the radiation from the cell phone tower is moving through the attenuating medium between you and there, the air and the walls and stuff like that. Your Wi-Fi reception, any of those kind of things, that's all Beer's law. It's a fundamental tenet of science, and you don't get to reject that. Okay? It's a bad look. It's a bad look to be rejecting fundamental tenets of science. Okay? There probably are people who do so. I have no idea who posts with the stock photo. But I'm sure that there are people who reject fundamental science, but they don't get to do that. Instead, we get to use something like Beer's law to talk about the flow of energy through the... I'm not going to take apart this diagram for you, but this is illustrating the flow of heat through the atmosphere, flow from the sun down to the surface, then heat given off by the surface, and then it flows up, and so on. And this is all just Beer's law. It's like juniors in college level physics. Okay? We can just do this. And what we find out is why the atmosphere is getting more warm, and I think we need a cute picture of a baby here. Because the baby's snuggly and warm because of his blanket. And Beer's law. The baby is giving off heat in the form of infrared radiation. If he didn't have a blankie, the heat gets out into the room. If he's got a blankie on, the heat is absorbed, that he's giving off anyway, is absorbed by the blankie. And then the blankie gives off heat, some away from the baby, but some toward the baby. The baby is warmer because the blanket is on him. Okay, that's a very simplified discussion of Beer's law. I mean, it's obviously way more complicated than that, but that gives you a pretty good sense. I mean, basically, these greenhouse gases that we put into the atmosphere are a blanket for the Earth. We actually need them. Without greenhouse gases in the Earth's atmosphere, Earth would be snowball Earth, it would freeze over into a permanent ice age, but we kind of keep overdoing it. Right? You know where we're going here. We call that the greenhouse effect. We're adding more and more of these greenhouse gases in the atmosphere to heat up the surface of the Earth. These greenhouse gases, most notably carbon dioxide, although there are others, are working to warm up the Earth exactly like a blanket warms up the baby. Okay? And it's not the kind of process that is, what the right technical term is, saturated. As in, like, if we don't add more, it doesn't, it isn't like we've got a warm enough blanket on the baby and adding more blankets. You got the baby crushed under a whole bunch of blankets. Adding more blankets doesn't make the baby any warmer. It's not like that. The more greenhouse gases we add, the warmer the planet gets. Okay? So, we better figure out what's up. What is physics telling us about these greenhouse gases? And while there certainly is a whole laundry list of them, the one we care about is carbon dioxide. Well, we care about all of them, but the one we're going to worry about today, because it's like burning of fossil fuels and so on, is carbon dioxide. We currently don't really have that much carbon dioxide in the Earth's atmosphere, only measured in parts per million, 405 parts per million. Pre-industrial era, it was 280 parts per million. And it is a very strong greenhouse gas. And we have been tracking it really well since the late 50s. And it has this big trend upward. Since the 1950s. That's this cool annual cycle, by the way. But the trend upward is obviously what we're alarmed by. Huh. Yes, it's getting higher all the time. We have passed 400 and we're on our way to, oh Lord, I wonder what I just did. There we go. Where do we get these things? Hey, calm down. Calm down. So where do we get all this carbon dioxide? Well, there certainly are a variety of sources. The two biggest that are approximately equal are transportation, fossil fuel powered vehicles, and production of electricity. Mostly coal-fired power plants, although there's also natural gas-fired power plants and so on. We don't have, well, they're not making carbon dioxide, are they? You're not supposed to be talking.
Oh, sorry.
And we got all these other sources that are by no means negligible, and we should be working on too. Just to show you how big the problem is compared to the natural climate system. We're going to be describing the amount of carbon in the atmosphere in terms of gigatons. Gigatons of carbon. So that's what GTC means. So this is some graphs that have GTC. How many billions of tons of carbon there are. And we can build some touchy-feely clip-arty pictures like this that shows that the atmosphere has a bunch of carbon dioxide in it. And for that matter, the land biosphere, I mean, plants store carbon in their tissues and so on. Or we could talk about how carbon is exchanged by photosynthesis and then sent back into the atmosphere by respiration. And in the natural world, these are lovely balanced processes. We have a carbon cycle. Or we could talk about how there's a carbon exchange between the ocean and the atmosphere. Carbon dioxide dissolves into the ocean very well. And we could talk about all these, and it's all pretty with clip art. But we got to be a little bit more scientific than that. We're going to put the reservoirs here, these little rectangles, the hexagons or whatever, just to show you here, though, that we have different places in the Earth system we can store carbon, but we have ways that it gets exchanged between there, like the land biosphere and the atmosphere exchanged by respiration and by photosynthesis. Whereas, like, the atmosphere and the big layer of the ocean exchanged by dissolving carbon dioxide in the ocean. But the whole thing, the whole Earth system exchanges carbon with rocks. We put carbon into rocks by, like, making limestone. We take carbon out of rocks by, like, chemical weathering of rocks and erosion and stuff like that. But look at the teensy number here. Oops, sorry. Look at the teensy number here. The natural rate at which carbon comes out of rocks, long-term storage, and gets pulled up in the atmosphere is practically nothing, and that's where we messed with it. Because we said, you know what would be fun? Cars, coal power, petroleum products. Let's pull it out at a rate of 9 gigatons a year. 9 billion tons. The world economy is over $10 trillion a year of fossil fuels. That's like 20% of the entire economy of the planet. I think. I might be doing the math wrong on that. All right. That's a huge amount of carbon that we're moving over there just by burning fossil fuels. Fossil fuels cut the corner on this process here, right? They take carbon that was in the ground in the form of harmless petroleum and coal and stuff like that, and burn it to do something useful, but then put the carbon dioxide in the atmosphere. And that's, of course, very bad. We're transporting huge amounts of it by all kinds of terrible things. When I look at the total amount of carbon emissions in the last 120 years or so, holy cow. Holy cow, we are not making any meaningful progress on this problem. Here, let's even break it out a little bit easier by what the sources of it. Oh, coal's dying. Oh, I wish. Coal, look at this thing. It's going nuts. Look at all these things. By the way, there's some carbon that comes out from making cement. But anyway, yeah, look at all this carbon here. This is, by the way, not as in how much carbon there is. This is the rate of growth over here on the side. Holy smokes. We're just transporting all kinds. Who's we? Well, the U.S. got a little better for a while. This graph actually ends in 2012. So you just see mostly the effects of the Great Recession. People not going to work. People not buying stuff. All right. The long-term trend in... Why does it do that every now and then? All right. The long-term downward trend in Europe is real. They've been working since about the 80s at decreasing their emissions. But obviously nobody, when we did things like wrote the Kyoto Protocol in the 90s, could have guessed China would go quite so nuts. Or India would go so nuts with their emissions. By the way, I wanted to be fair. Burning fossil fuels is not the only way. I'll talk to your question at the end, okay, buddy? It's not the only way we're getting carbon from other sources back into the atmosphere. Obviously, just forestation, for example, is one. But this is, orders of magnitude smaller than the fossil fuels. All this just tells us what's going on. It doesn't tell us what's going to happen in the future. That's the answer we want. We want to know what this is going to mean. What are we going to do with this? We need a way, and the tool science uses to figure out what's going to happen is called models. These are going to be numerical models. Models could be like, a model of an aircraft in a wind tunnel or something like that, or a model of a bridge that they're building as part of a... This is not. This is a computer program. I like to tell my students when we learn about numerical models to think about video games. How about a video game of cars? A video game of cars is a computer model of cars, like a car racing game. Because it wants to know the real physics of how the car moves. If the car can go from 0 to 500 miles per hour with no limit in range, can stop on a dime, can turn on a dime, and can fly with its gun on the front that never stops shooting, it's not much of a fun game, right? The game is fun because it's real. The car has to slow, it has to slow down, right? The game knows the physics of the real system, in that case the car. We're going to be making a computer program here that runs on these big old supercomputers that knows the actual physics of the atmosphere and the climate system to make predictions of what the climate system is going to do. This should be astounding. Let me give you an example of how this should be astounding. Has anybody here ever been to like one of the Gothic cathedrals of Europe, like Notre Dame or the Kölner Dome or something like that? Okay. When you step into it, unless you're a terribly jaded soul, your first reaction should be, how the hell? How in the hell did we even conceptualize something like this? How, sitting in the 11th century, did the architect even think of something like this? How did he even think of something that the technology to build wouldn't even be around? Can you imagine the meeting with a contractor? It's like, thank God I'll be dead before we have to figure out how we're doing that rose window. Right? The things took centuries to build. I cannot conceptualize a building that will take us 200 years to build and need technology 200 years from now. It is a staggering achievement of the human mind that we can build a Gothic cathedral. Climate models are the Gothic cathedral of science. They are the most I'm sorry to disappoint you, they are harder than particle physics, genomics, economics, AI combined. Climate models are the top tier of what we've ever achieved as humans in science. They have put together, it is the Gothic cathedral. Starting 50, 60 years ago, scientists started putting together the idea that at some point we should be able to make a prediction of time. We should be able to write computer programs. The computers didn't exist yet. But they said they're on punch cards. Don't use me like that. And they were able to conceptualize that someday we'll be able to do this. Let's start developing the equations, the algorithms. They're going to be able to describe all the physics of the forces acting on the atmosphere, and the kinematics of gases, and the gas phase chemistry that's going on, and the radiant transfer, and put all that together in a way that works to simulate the climate system. These climate models are tens of millions of differential equations, all being solved simultaneously to make a forecast of the weather or the climate like 2 seconds from now. And then do it again, and then do it again, and then do it again, iteratively, tens of thousands of times. These things take a supercomputer weeks to months to run. This is the most staggering thing humans have ever tried. And it works. And it has become our fundamental tool for understanding the climate. Not just future climates like what global warming is doing and so on, but frankly, anything any climatologist does, because he likes to be interested in a dorky scientist and wants to know how the climate was changing at the end of the ice age, or how this would happen, or how this new reservoir will affect the regional climate of its area, or whatever. We run these climates. We run these simulations. We simulate the climate with like a control run, and then we change something, and we have an experiment run. It's science now. The staggering achievement is normal science now. It's how we do things. These numerical models of climate are dangerously, maybe very closely, I don't know exactly what word to use, close to what numerical weather prediction is. The guys on TV. The guys on TV have an easy job. There aren't any meteorologists here, are there? Okay. Guys on TV have an easy job. Because they're not making those forecasts. Whoever your favorite TV meteorologist is, he ain't making those forecasts. The companies that he works for, they have contracts with companies that make these forecasts using these models. He interprets that information, puts it into context and so on to help you understand it. Okay? Those models are basically the same as these climate models. They just run for to make a forecast for 24 hours from now, or 48 hours from now, or 72 hours from now. But you would not be a horrible human being if you make yourself feel a little skeptical about this, because everybody hates meteorologists. I can't blame you. I often don't care for them either. Because they often blow it. And people get skeptical. Meteorologists don't know what they're doing. Their computer programs don't work at anything. And so you're not a bad person if you say, wait a minute, how can they make forecasts of what the climate is doing 100 years from now if we don't know what the weather's doing on Thursday? Okay? That is a perfectly valid question I'm setting up as a straw man. And let's talk about what's wrong with that. And we're supposed to be talking about how we know what we know. Well, the answer is, even though that sounds like a reasonable question, it's missing the point that questions about climate and questions about weather are two very different types of questions, and they take two very different types of answers. And that's not obvious to the public. The first one's a little bit of a wonky thing. It's actually really interesting. Anybody who had the misfortune of having to survive differential equations or some other high-level math class learned that there's two different types of these differential equations, the initial condition and the boundary problem. Turns out weather forecasting is an initial condition type of problem. Boundary condition problems are more like what climate is, and they have very different strategies for solving them. I'd love to walk you through an example of that. I don't want to do that right now, though. She said, please don't. On the other hand, they have very different answers. The weatherman wants to know very specific conditions at some very specific location at a very specific time. The climatologist does not care about that. I do not care what it is doing 100 years from today. I care what the 2120s will be like. Right? I don't really care what those models, they can't tell you what 100 years from today is going to be like, but they can tell you what the 2120s will be like. Okay? It's a very different kind of answer. Even more horrifying. If I just, went to Jonathan and said I want funding so that we could have the Ivy Tech Center for Climate Modeling, and he actually went and got us a supercomputer, because it could happen.
Yeah,
it could. We could run a model. And we can make forecasts of climate using that model. That's called deterministic modeling. That's a word here that means we've determined this model is the right choice for us.
Hey,
Yes.
remember
Yes, I thought about that too, even as it was coming out of my mouth. That is, in fact, not how it's usually done. What we usually do is what's called ensemble modeling. I'm sorry, Jonathan, but we're going to need lots of supercomputers, probably 30 to 40 of them. Okay? The forecasts that you see on TV, that meteorologist you don't trust very much, they probably ran 20 or 30 versions of the model with slightly different assumptions, slightly different initial conditions, and so on. To build this ensemble of forecasts, 30 different forecasts of what the weather's going to be like tomorrow. That sounds like a nightmare. But actually it's brilliant, because this gives you a range of possible outcomes. We now have 30 different answers about what's going on tomorrow, but we kind of have a sense of what's the consensus? It was a powerful vocabulary word. What's the consensus between all these different forecasts? And what's the range? Well, that's kind of the information we want about. I don't know if that's what we want for Thursday, but that is definitely what I want to know about for climate. I want to know not just what's going on now, but what is going on, like what's the range of possibilities for the future? And what's the most likely one? And that's where we get these kind of diagrams, which you come back to from the beginning of the talk, where we have made forecasts of the global mean temperature for the next 100 years. And there are different scenarios here where we have run the model with slightly different predictions, that I'll talk about them in just a little bit, but different predictions about how much greenhouse gases we're going to emit. But for each of them, we ran these models about 45 different times. Slightly different assumptions, slightly different. So that's why there's like these bars on here. So for example, for the B1 conditions, which are the most optimistic conditions about us getting all crazy about getting rid of greenhouse gases and stuff like that, we have a range between the warmest model and the coldest model after 100 years. And like for other sets of conditions about how less optimistic we are about how we're going to reduce carbon dioxide, we have a range. We have both a consensus, which is the darker part here of its prediction, and the range as what it's going to be. Let me talk to you about some of those forecasts. Here, I'm going to stretch this out so that it fits over here so you can see it against the scale better. B1 is the most optimistic. This is the kumbaya. Earth Day 2019 is where we're changing the world, and we're going to stop emitting as much as we can possibly do. We're going to get this fixed as fast as we can. And if that happens by the year 2100, we'll only have 1.8 degrees of warming compared to the year 2000. That doesn't sound so bad. Ain't going to happen. Sorry. We aren't that happy. Maybe we can have this better one. Here's A1T. A1T is a scenario that says we're going to go nuts on solar and wind and all kinds of geothermal power and stuff like that. We're going to spend money on technology that makes things better. It's going to take time, but we're going to do it. We're going to share it with the world. We still end up with about 2.2 degrees of warming. That's a lot of warming. We've blown right past the Paris Climate Accords. A1B is business as usual. Business as usual means we're going to keep finding fuel. We'll find someplace else to have an oil field. We'll keep it, oh crap, start getting up around 3 degrees Celsius. 3 degrees Celsius is the range where we're starting to get worried about whether society can survive. Bad news, it gets even worse. A1FI is the fossil intensive. Fossil intensive is the prediction that we will be throwing money and technology at finding more and more horrible ways to find fuel, like fracking and tar sands and things you've heard of, because guess which one we're on? A1FI. We throw money at making sure gas doesn't go over $2.50 a gallon. Right? We are actually, by the way, in terms of the emissions that were predicted by A1FI, we're actually running ahead of it. We are actually worse than worst case scenario right now. Oh, by the way, notice that gets us all the way up to 4 degrees Celsius, with some of the models predicting as much as 6.5 degrees Celsius of warming. We're so in trouble. We're so in trouble. We don't know how to make any of this, and boy, we don't want to be to blame. Boy, we really want to find something that this could be other than us. Because climate is complicated. And we really want to find something to blame about this, and he'll be fine. He looks good. I don't think he's going to drown.
He can swim.
He can swim. Let's find something to blame. I mean, is any of this stuff proof that we're what's causing it? Or that at least our greenhouse gases are what's causing it? Well, proof is a tricky word. Philosophers of science would tell us that things like modeling and so on, this is not strictly speaking proof. We're not doing an autopsy on the climate. We're not running a controlled experiment like let's have one Earth where we do this and one Earth where we don't. This, strictly speaking, is not proof. But it is about as close to proof as we're going to get. It's a smoking gun. When we take our climate models and start them instead of at the year 2000, we start them at the year 1900, and simulate the climate of the 20th century, we get almost exactly the warming we observed. The model says that the Earth should have warmed by about 1.2 degrees Celsius, and the real world warmed like 1.25 roughly, or something like that. That's a hell of a smoking gun. Science works. It's unlikely that we just made these mistakes and like somehow or other overestimated this by exactly the amount we overestimated this, and it just so happens that just what those greedy liberal scientists want is we got exactly the answer that they all wanted. No, that's the way it works, right? Science works. We should be able to make this. More importantly, this is the best answer we're going to get. It isn't like, oh, I'm going to wait till the science is an answer anymore. All we're going to have is more and better model runs. Grimmer. Is grimmer a word? More grim. We aren't going to have a better answer than this. If we can't make policies based on these answers, we can't make policies at all. We're just failing. It's not the sun. Man, I can tell you how often, I taught this class many semesters to freshmen. Every 18-year-old is pretty sure he knows what solves climate. It's not changes in the sun. We have whole systems that measure solar output for like operations of solar panels on satellites and things like that. We have monitored things like sunspots for 300 years. We know that it's not the sun that's causing this. We know it is not the tilt of the Earth's axis. Oh, I don't love that answer. There's definitely a whole group of people out there who believe that that this global change is actually the Earth's axis is tipped. I'm not sure how they think telescopes work if the Earth is tipped and we don't know it, right? Telescopes work because you can point them in a very specific known direction. If the Earth is tipped and we somehow missed it, I'm not quite sure how they think that would work. It's not a cycle. Oh my gosh, my father-in-law loves to say that it's a cycle. It's not a cycle, all right? There are cycles in climate, like ice ages, and the Milankovitch cycles, which are controlled changes in the Earth's orbit due to like Jupiter's gravitational effect. And there are cycles in year-to-year climate variability, things like El Nino and so on. But these things can be shown to have the net effect of the whole cycle is zero. They're a type of weather phenomenon called internal variability, and they can be proven that the net effect over the cycle is zero. You can't make the planet warmer by having an El Nino event in the Pacific Ocean. More importantly, if it was a natural thing, why is it happening now? Here's the last 12,000 years or so of climate records. See this little spike? That's like the last 70 years. Well, why the hell now? Why not here? Why not here? In fact, we can extend this by different paleoclimate records back hundreds of thousands or millions of years, and this has never happened before. It's pretty hard to blame it on something natural if there's never been seen before. What would be causing it if not us? So what we saw here was we saw that he's got answers, I know. Welcome to my life. Welcome to my life. So what we saw here is there's no shortage of evidence. It is not something we get to be skeptical about that the warming is happening. It is not something that maybe we don't understand the physics. I suppose if you want to be unsure about the climate, the modeling, I guess, I don't know. But we know a whole lot of things that's not too. Now what you're going to do about that, that is a whole complicated, that could be a different day. But it's not good. And it's not going to get better. What's the line from the Lorax? Unless someone like you does a whole awful lot, it's not going to get better, it's not.
The Earth is about the local warming.
Yes.
And pollution.
It's not going to get better on its own. We have to make decisions about what we're going to do about it. But that's why I gave the talk, is so that we have information and we can do it together. All right, that's all I got. Can we let him ask a question? I can answer yours later.
Any thoughts about technology being developed to sequester CO2?
Oh yeah, sequestering CO2. What was it? Slate or something just the other day had a whole article about sequestering technology. This is the idea that we should capture carbon dioxide and not put it into the atmosphere. It's extremely difficult to figure out how to store it is the problem. If we just store carbon dioxide, the problem is it'll eventually leak out. I mean, we can't put canisters of carbon dioxide someplace. It's very hard to find a stable way to store carbon dioxide so that it doesn't just get back out. There are some technologies that are coming about that currently are ludicrously expensive, but the study that was out this weekend about that talked about how like you can kind of project forward roughly what the eventual cost of carbon sequestration technology would be. And ballpark, carbon sequestration will cost approximately about as much as the fuel itself did. So if we currently spend worldwide about $10 trillion a year on fuel, this would be about $10 trillion we would be spending on the expendables and stuff like that associated with carbon sequestration. That's not a small commitment just to keep running in place. You know what I'm saying? 10 trillion a year would just get what we're putting in that year into, sequester that. We got 75 years of before that, since World War II, of trying to figure out how to fix things. It's not really a great choice. Yeah.
I need to say that if we make everything with electricity or anything like that, so like for example, it's like cars that can run in electricity, like a electric stove or something like that. If everything is in an electricity, will this help the climate at all?
Yes, that's a great question. Because she wants to know if things like electric cars and electric stove, is that better? And the answer is yes. Even if the electricity is coming from a carbon-intensive source like coal, it's much more efficient to produce it at a fixed site and transport the energy than to, say, have a gas-powered engine in your car. Okay? Gasoline-powered cars produce far more carbon emissions per mile you drive than the carbon emissions it took to make the battery that charged the car. Okay? A stationary source can be run much more efficiently and so on than. So yes, that's part of the reason why coal isn't going away anytime soon. We're going to know any kind of solution that we're going to do this is going to involve many times more electricity than we produce now. And we won't be able to afford to get rid of coal. We're going to need that for a long time. Yeah.
I was going to ask, because I've heard a lot of different answers on this. I've heard some people say, well, we're at the point where we can't really reverse it, and other people say it's very critical that we change now. So,
Yeah, okay.
Are we at a point where climate change is so severe that the only thing we can do is slow it down?
Yes. Climate change by carbon dioxide is what's called an irreversible process. Okay? It's not literally irreversible, it's that it would take many times longer to fix it to get the carbon dioxide back out than it took to put it in. So, like, for example, natural processes will continue to extract carbon dioxide. Things like the growth of forests and so on would remove carbon dioxide, but it would take on the order of several thousand years to take the carbon dioxide out that we've already put in just since, like, World War II.
So, for lack of a better way of wording this, what are the chances that we're going to be screwed because of this?
What are the chances we're going to be screwed? I love that question. I would say 100%. No, well, I mean, it's going to be, I mean, that's what life is, right? It's coping. Adaptation, mitigation, that's life, okay? It's just that we're deciding what future generations have to mitigate and have to deal with. And I think that we can make the situation better. We can do things like electric vehicles. We can do things like solar power and make things better. If I don't give him, he's going to have an aneurysm here. What's going on?
So can you go back to that one graph over there? Because there's a part that I don't understand.
I'll talk with you about it afterward, okay? Because I know you have lots of questions. Yes.
Yeah, about 50.
I have a question. Do the government or I'm sorry, I didn't mean to talk about.
No, I'm excited.
But do you think that like car dealerships or any of the cars, are they planning to create like electricity car or changing it now, or what's going on?
Well, I mean, almost every car manufacturer has plants that are making electric vehicles now, right? You can buy an electric minivan from Chrysler. You can buy there's several different fully electric vehicles from BMW. There's a Chevy Bolt that's fully electric. There's the Tesla vehicles. If you want an electric vehicle, you can buy it now, okay? They're waiting for the demand. You know what I'm saying? The demand from the public is what will make car manufacturers and truck manufacturers make more of those. So we kind of have to, we get to decide, right? If we make demand for those kind of products, or we say we're going to create tax incentives for those kind, the $7,500 tax credit for an electric vehicle is about to expire. If you want to buy an electric vehicle, do it real quick. All right? I mean, we really need policies like that to get people into the right choice.
Will I'm saying, will we see that process going to happen?
I
in the
think
next couple of
electric
years?
vehicles are pretty much a done deal. I think that will happen.
Okay.
Yeah. Go ahead. Why not?
So I have a question.
Yes.
Is there going to be another ice age, or is the global warming going to make there no more ice age?
Yes, that is a great question.
So no more
The short man
mammoths?
in front had a great question. Yes, we have now had enough greenhouse gases with enough radio forcing in the atmosphere. We are actually just in terms of changes in the Earth's orbit, we're tipping toward an ice age right now. I mean, it's still, 2,000-3,000 years away or something. But we already have enough greenhouse gases in the atmosphere. Even if we all left the planet on spaceships today, there's enough greenhouse gases in the atmosphere, the next ice age isn't going to happen. Until we get the carbon dioxide out of the atmosphere by natural processes, there won't be any more ice ages.
So no
Well,
more
naturally. Don't
So
get me
no
started
more
about global
mammoths?
thermonuclear war and things like that.
What? So no more mammoths? And what is global thermonuclear?
My understanding is some of the satellite data and stuff is not the same as what we get from surface. And,
Yes.
and that there is a pretty large difference between the satellite data on temperature, and I know that they're done by mathematical formulatures and they're indirect.
Yes.
Can you explain a little bit?
Yeah,
how
well, that's
that-
always
how
a
that
challenge.
works?
Because you're right. Satellite data, hey, buddy, you have to be better behaved than that. Okay. Yes, you're right. It is not a perfect match of the surface data to the satellite data. The satellite data is always averaged over a little area, over a, like a volume of air. It is actually quite mathematically tricky to recover the temperature from those the radiometer's measurements that it took up in space. There's always calibration issues that have to be corrected and stuff like that. And it's usually not a perfect match. So usually the surface data is considered the ground truth. And then the satellite data are calibrated to match that. So that we can keep, we can recover the pattern of the temperature changes from the satellite. It fills in the gaps between the surface observations, but they're usually keyed so that they, at the location of the surface observations, they match. That's a whole process. I can't think of this name right now. I'm going to talk to you more afterward, okay? Because they got lots of questions here.
Probably this is. What is it? Global war?
Global, yeah, okay, I'll talk about that later, okay? Yes, you have a question.
If you don't mind me asking, I know that there are a lot of people that are so skeptical about climate change that it's just become a political statement.
Yes.
What I was curious about was what are some ways that you think that we could maybe stop it from being a political statement and bring it back to just being like, I'm so bad at explaining things.
No,
I'm
no.
sorry.
No, that's brilliant. I don't have an answer for that. I mean,